Okay. So today our topic is induced representations. I believe this is the 10th lecture. We've got two more, and then we're done with Steinberg. Okay, so if f is a function from G to C, so it's part of the group algebra, then we can restrict f to H, a subgroup. So H is a subgroup of G. And this gives us a map, which we'll call the restriction map from G to H of F. I think one of the biggest problems with this chapter is this very clunky notation, but I don't know, it might be necessary. I couldn't think of a way around it. So this is called the restriction of F, and the way it's defined is, well, it acts on an element of H, and what does it give us? Well, it just gives us F of H. Okay, so right off the bat, here's a proposition. Let H be a subgroup of G, then this map, this restriction map, takes a class function to another class function. Ooh, run out of space. C of L of H, and is a linear map. So remember, class functions were these functions that gave you the same output for different elements of the same conjugacy class. So if I take a conjugation of the argument, the function is still the same. Okay, so I think for everything today, I'm not going to prove any linearity. I assume you guys can check linearity. And I'm just going to check that this thing actually takes a class function to a class function. So let f be a class function on G if x and h are elements of H, then we just got to do the calculation. The restriction of G to H applied to f of x, h, x inverse. Let me fix my notes really quick. Is equal to, well, this thing is an element of H, and so this is just f, x, h, x inverse. But f itself is a class function on G, so that implies that this is f of H. And so this is the restriction of G to H of f applied to H. And so that tells me that this restriction map is taking a class function to a class function. Okay, so can we obtain a linear map that goes in the other direction? So can we obtain a map that takes a class function on H to a class function on G? Well, to do this, I'm going to give you a little notation. So let's define f dot from G to C. So f here is meant to be a function from H to C. This is a class function on H. We can define this by f dot of x is f of x when x is in H and 0 otherwise. That seems like the pretty obvious thing to try. And well, the assignment that takes you from F to F dot is linear. It's a linear map from functions on H to functions on G. I think I said this is a class function earlier. This can be any function on H. And what we'll do is we'll now use this map to assign a map on the class function level. So we have a map on the group algebra level, and now we want to move to the class function level, which is the same as the what's it, the commutant, the centralizer. That's what it is for algebras. The centralizer of the group algebra. Okay, so the map called the induced map is defined this way. So we see this kind of averaging trick sort of come in again here. We're only averaging over H, even though we have all the elements in G listed here. But this is called induction, or the induced map. So when it's applied to something, the result is the induced map. So if chi is a character, then the induction from G to H of chi is called you guessed it, the induced character. Well, the induced character of chi on G. So we're going to show later that this is in fact the character of a representation. Just take my word for it for now. We will come back to that. So again, let H be a subgroup of G. Then the map of the induction, or the induced map. Induction map? Yeah, the induction map is linear. Okay, so again, I'm not going to show linearity. I'm just going to show that it takes the class function to a class function. Okay. So let f be a class function, I forgot the z, on H, and let y, g be elements of G. Then what we have is the induced map, H to G, f of y inverse G y is 1 over the order of H, the sum over x and G, f dot x inverse y inverse G by x. So this is the definition of the induced map. And this is equal to 1 over the order of H, the sum over Z and G. I'm doing a change of variables here. So we're setting Z equal to YX. And then this is equal to the induction from H to G of F applied to G by definition. Okay, so that shows that the induction map sends a class function to a class function. All right. So we now are going to come to a theorem which is known which is known as Frobenius reciprocity. Write that down. And what it says is that the maps, the restriction map and the induction map are adjoint to each other. So in practice, if chi is an irreducible character of G and theta is an irreducible character of H, so let me write that down. So in practice, what this says is that if chi is an irreducible character of G, theta, same thing, but of H, then chi inner product with the induction from H to G of theta is equal to the restriction from G to H of chi inner product with theta. And so the multiplicity of chi in this induced map is the same as the multiplicity of theta in the restricted map. Okay. So let me just prove this inner product here, inner product identity. So let me be consistent with my notes. What I'm going to prove is I don't want to mess up later and write A and B versus chi theta. So I'm just going to change everything to A and B right now because that's what's in my notes. So I want to show that this equality holds for any class functions A and B. Well, I should specify A is a class function on H, and B is a class function on G. Okay, so how do we show this? Well, start from some definitions. So this is 1 over the order of G of the summation over G of the induced map applied to A, applied to G, B applied to G, complex conjugate. So this is my definition of the inner product. And this is equal to, good. So now I'm going to apply the definition of the induced map. Okay, and now I'm going to go ahead and switch the order of the summation. I'll take both of my constants out here. Now, notice that A dot x inverse gx is not equal to 0 if and only if x inverse gx is in H. So that's the definition of this dot function. So that's the same thing as saying that G is equal to XH X inverse for some H. Well, then this thing we're trying to compute must be equal to 1 over the order of G, 1 over the order of H. Put our sums in here again. And now this one I'm going to re-index H. And now my summation is over H due to this property here. And I need more room. So do this. And this is going to be 1 over the order of G, 1 over the order of H, summation over X and G, summation over H and H, A of H, and then this is B of H bar, because B is a class function on G. Okay, and then this is equal to, so I'm recombining some things. This is an inner product. So right, we can replace this B with the restricted map because from G to H, because well, B is only acting on something that exists in H. And maybe I don't need any more space. And this is just equal to exactly what we wanted. And so that proves the theorem. Okay, so the point is that this restriction map and this induction map have this nice property that they are adjoint to each other. And so the multiplicity of one character and the induction of the other character is equal to the restriction of the previous character. So the multiplicity of theta, the second character in that first one. Okay. So this formula I'm going to now prove is often pretty useful. Again, let H be a subgroup of G. Maybe I should just state H is a subgroup of G always. I'll probably continue to write it, but let T1 through Tm be a complete set of representatives of the left cosets of H and G. Okay, then the following holds. The induced map acting on G is the summation from I equals 1 to M of F dot on Ti inverse G Ti. And this holds for any F, a class function, other way. This should be Z. Z, L, H. So this formula is nice. It gives us the induced map while only having to conjugate by the representatives of the cosets of H rather than by all of H. So this is equal to by definition 1 over the order of H, sum over X and G F dot X inverse G X. And so this is the sum from I equals 1 to M. And we can write this as, well, okay, so I'm rewriting this whole sum here as a double sum. And the reason this holds is because, well, G is partitioned by the left cosets of H. And so every element of G looks like TIH for some TI, one of my representatives, and H, and one of the, well, in H. And so summing over the elements of G is the same as summing over all possible combinations of a representative and an element of H. Okay, and now this is equal to the sum from I equals 1 to M F dot TI. Ooh, no, I'm skipping steps. Okay. Okay. So with H, an element of H, we have the following. H inverse TI inverse G TI H is an element of H. We care about when this is an element of H, right? Because of this dot function here. That's going to tell us when this thing is 0 or not. This is in H if and only if TI inverse GTI is in H. Why? Because, well, H and H inverse are already in H. Okay, but if F is a class function on H, then F dot H inverse TI inverse, let me pull this up, G TI H is equal to F dot TI inverse G TI, right? Because it's a class function on H. And it follows that the induced map, so using this information, it follows that the induced map has the following form. Right, that's using this property here from here. And now this is equal to 1 over the order of H, the sum over H and H. So I'm switching the summation. And now this is exactly, so we have no more H's here. I just sum over all the H's. How many do I have? Well, it's order of H. So this is just the sum from I equals 1 to M of F dot TI inverse G TI. And that's the case proof. Okay, so if I want to know the induced map, I don't have to conjugate by everything in G here. I just have to conjugate by the representatives of the cosets of H and G. Right. And I can also get rid of the averaging, so that's nice. Okay, so let's apply this methodology to the theory of representations. So all we've talked about so far is class functions and characters. So let phi be a representation of G, and as usual, let H be a subgroup of G. Then we can again restrict phi. So, well, I shouldn't say again, this is the first time we're doing this. We can restrict the representation phi to the subgroup H to obtain another map. From H to GLV. And moreover, if H is an element, if H is an element of H, then the character of this restricted map. So I haven't said that this thing is a representation yet. It is. We'll show that later. But the character of that representation is actually equal to, well, it's the trace of the restricted map at H. And this is the trace of phi of H, right? Because how does the restricted map act on an element of H? Well, it just applies phi. And this is equal to chi phi H, which is the restriction from G to H of chi phi acting on H. So in other words, the character of the restricted representation is equal to the restriction of the character of the original representation. So this restriction map kind of factors through the character. Okay. So our next goal is going to be to show that induction also sends characters to characters, but this is going to be a lot more complicated to prove. So let's look at some examples first to kind of get an idea of why that's the case. But the analogous map will hold as well. So let's just take something really simple, like chi1 be the trivial character of the trivial subgroup. Trivial subgroup 1 of the group G. Okay, so I need to unpack these words. Trivial. The trivial character is the character of the trivial representation, right? Which is the representation that sends everything to 1. And the trivial subgroup is just the subgroup with only the identity element in it. So then the induced map from the trivial subgroup G of chi1 applied to G is the sum from over X and G, chi1 dot X inverse G X. But X inverse GX is in the trivial subgroup if and only if G is equal to 1. So that tells us that this induced map is the sum over X and G of chi1 of 1 if G is 1, or 0 if G is not 1, right? That's the property of the dot map. And then this is just, well, chi1 of 1 is just 1, and so this becomes the order of G if G is 1, and 0 if G is not 1. So the induced map from 1 to G of chi1 is the character. So you might recognize this particular character. This is the character of the regular representation. So remember, the regular representation is one we learned about last time. That came from, so we had the group action of left multiplication, and the permutation representation associated to that group action was called the regular representation. And we found out that that regular representation is, I think, never irreducible. Okay. So the induced map, well, the induced character of this irreducible representation, which is the trivial representation, is in fact reducible. So irreducibility is not preserved by this induction process. Okay. So let's do another one. We can generalize that last one slightly. So let H be a subgroup of G, and consider the associated group action sigma from G to the bijections of the cosets of H and G, given by sending XH, this coset, to GXH. Okay, so notice that XH is fixed by G if and only if GXH is equal to XH, definition, if and only if X inverse GX is an element of H. Now, there are order of H elements, X, giving the coset XH. So the size of this fixed set is 1 over the order of H times, I need more space, times the number of X and G such that X inverse GX is an element of H. So again, let chi1 be the trivial character, but this time let it be the trivial character of H. Then chi1 dot of X inverse GX is 1 if X inverse GX is in H and 0 otherwise. And so chi sigma tilde of G, so that's the permutation representation induced by this group action, and we're taking that representation's character. And remember, for the regular representation, we showed that this was the order of the fixed set. That's why we're talking about this. And so this is 1 over the order of H, the sum over X and G of chi1 dot X inverse GX, which is equal to the induced map from H to G of chi1. So this is for any G and G, and so the induced character of the trivial character is, in fact, the character of the permutation representation, sigma tilde. Okay. So we're ready to define now what the induced representation is. So let M be the index of H and G. If you don't know what this means, this is the number of left cosets of H, G. So if H is a normal subgroup, then you can take this quotient G mod H, and the order of G over the order of H will be the number of cosets, right? And so the index will be order of G over order of H. But if H is not a normal subgroup, then we can't take the quotient and get another group, and so that doesn't hold. So without loss of generality, let's assume that, well, first I have to collect representatives. So first of all, choose a complete set of representatives again. Let's call them T1 through Tm again of the left cosets. Okay, now without loss of generality, let's assume that T1 is equal to 1. Why? Because, well, the identity is in one of these cosets, because the coset partition G, and that coset can be represented by anything inside of it. So we might as well let it be the identity element. Okay, so suppose phi from H to GLDC is a representation of H. So notice we're thinking of the representation in terms of matrices now. And define phi dot x to be phi x if x is in H, and 0 if x is not in H. So here, 0 is the D by D 0 matrix, right? Because this thing needs to be an element of GLD. Okay, so the induced representation of H to G of phi from G to GLMD of C is defined as follows. In matrix form, we have, I need to give you some notation. This map here, I'm going to call phi G, just to save a little space. Okay, so this phi G evaluated at the group element G is equal to the matrix phi dot T1 inverse G T1, phi dot T1 inverse G T2, phi dot T1 inverse G Tm, and we continue in this way down to the last row, which is Tm inverse GT1 all through phi dot Tm inverse GTm. So in other words, phi G G IG is defined component-wise, like so. Okay. So before we actually show this thing is a representation, maybe some examples are in order. I'm just going to do one actually, which is the dihedral group. So the dihedral group, remember, was the group of all the rotational and reflection symmetries of some polygon. let G be the dihedral group. En, this is the one of order 2n. So if R is a reflection, actually, no, I want to be consistent with my notes. I call this a rotation. And I call S a reflection. Then the dihedral group of order 2n is the collection of all elements of the form R to the M, S R to the M, such that 0 is less than or equal to M, is less than or equal to n minus 1. Okay. So let H be the cyclic subgroup given by the rotations. This has order n, and its index is 2. That's the index of H and G, 2. So for 0 less than or equal to k, less than or equal to n minus 1, let chi k from H to C star be the irreducible representation given by chi k r to the m is equal to e to the 2 pi I k m over n. So remember the abelian groups, which a cyclic group definitely is, are very easy, right? Their irreducible representations are given by products of these characters. Well, that's not a wrong thing to say. The character is the same thing as the representation when the dimension is equal to 1. But anyway, the point is for abelian groups, the representation theory is very simple, right? We have this character given by the roots of unity. So we'll now compute the induced representation, which we'll call phi k of the kth irreducible character. Okay, so the way we do this is we want to choose coset representatives wisely. So let's take ti equal to 1. Sorry, that should be a 1. T1 equal to 1 and T2 equal to S. So the index of H and G was 2. So there are 2 cosets, and I am telling you that 1 is in one of them and S is in the other one. And now I'm choosing those as my representatives. Okay. So then T1 inverse R to the M T1. So we could do all of these multiplications. T1 inverse R to the M T2 is R to the M S, which is S R to the minus M. And so you could go through these and figure out what all these products end up being. I'll write down maybe one more. So you do the same thing for S R to the M. Okay. This comes out to S R to the M because T1 is identity, right? And you just keep going down the list like this. And what you obtain is that phi k evaluated at Rm is, well, this is chi dot k of R to the M, chi dot k of SR to the minus M. So this came from here, this came from here. Chi k dot of SR to the M, chi k dot of R to the minus M. So again, came from here, came from here. And this is e to the 2 pi I k m over n. This is 0, this is 0. This is e to the minus 2 pi I k m over n. And so there is our representation of r to the m. We can also do the kth induced representation applied to SRM. And I'll just tell you what we get here. We get 0 e to the minus 2 pi I k m over n. We get an e to the 2 pi I k m over n, and we get a 0. Okay. So that was the induced characters of the the induced representations of the irreducible representations of the dihedral group, or at least the yes, okay, I said that wrong. So we have these characters and representations of the cyclic group, which is a subgroup of the dihedral group. And we want to get an induced representation on the entire dihedral group. And those representations are given here. Okay, hopefully that was less confusing the second time around. All right, so next theorem. So again, H subgroup of G, and we're going to assume that the index of H and G is M for notational convenience, and suppose that phi from H to GLD, C is a representation. Then the induced map from H to G on phi, which maps from G to GL MD by definition. This is a representation. And moreover, the character of this induced representation is just the induction of the character of the original representation, just like the restriction map. Okay, so here's the proof. So again, T1 through Tm representatives of the cosets of H and G, and we're going to set phi G to be, again, the induced map. There's a reminder of notation. And we're going to start by showing that phi G is a representation. So let xy be elements of G. Then what we need to do is we need to show that phi x, G, phi y. So our definition is in terms of matrices. So we need to write this in terms of matrices, or at least their entries. We want to show that this is the same as well, yes, we want to show this is the same as phi g x y, and I'm missing a g here. The ij entry. Okay, so this is equal to the sum from k equals 1 to m of phi x g I k, phi y g k j. So product of matrices, right? And this is equal to the sum from k equals 1 to m of phi dot Ti inverse x tk, right? And then phi dot tk inverse y tj. Okay. So that was our definition of phi g. The only way that phi dot tk inverse ytj, the only way this guy is not zero is, so this if and only if tk inverse ytj is in H, that's the definition of this dot mapping, or equivalently, tkh is equal to ytjh. Okay, so ytjh, well, this is a coset. It's not necessarily the coset with representative tj. We don't know what the representative is. Right? So let's just call it TL. So if this is the representative out of the ones that we chose, of the coset ytjh, then, and I'm gonna label this guy so I don't have to write it again. Then the sum from k equals 1 to m of phi dot ti inverse x tk, phi dot tk inverse x tl, sorry, no, tj, is equal to, so that's this guy here, is equal to phi dot ti inverse x tl, phi tl inverse ytj. So where does that come from? It comes from this property here. So all other terms are zero. But this is non-zero. This is non-zero if and only if ti inverse xtl is in H, if and only if tih is xtl, whoops, that should be a tl h, which is xytj h, if and only if ti inverse xytj is an element of H. And in which case, so and if this bottom thing is true, then we have that one, which was this guy that we're concerned about, is equal to phi ti inverse xtl phi tl inverse ytj, which is phi ti inverse x y tj. So this is because phi is a representation, which is a homomorphism. And so that implies that phi x, phi y, g, ij. So the product of the induced representations is in fact phi dot ti inverse xy tj, which is equal to phi xy g ij. Okay, and so that implies that phi g is a representation. Okay, that was a little tricky, but oh, we still have one more thing to prove. we need to show that the character of the induced representation is the induced character. But that part's actually pretty easy. Chi phi g is the trace of phi g on g, which is the sum from I equals 1 to m of the traces of phi dot ti inverse g ti, right? Because yes, okay. Yeah, this thing is a matrix, right? So the trace of the larger matrix, which is the induced map, right, is the trace of all the things down the diagonal, which are these guys, which is the sum from I equals 1 to m of chi phi dot ti inverse g ti. Okay. Yes, good. And this is the induced map from H to G of chi phi. Okay. So that's all well and good. But from our examples, we saw that given an irreducible character, chi, of some subgroup H, there's no guarantee that the induced character will be an irreducible character, meaning that the induced representation will be irreducible. There's no guarantee. So on the other hand, sometimes induced characters are in fact irreducible. They're not always reducible. And our goal now is going to be to understand when this is the case. So by Frobenius reciprocity, remember we have the induced map GH chi phi inner product with the induced map GH chi phi. This thing by Frobenius reciprocity will be equal to chi phi inner product with the restriction of the induction of chi phi. So this just says that induction and restriction are adjoint to each other, and so that's all we did here. And now we had a proposition when we first started that said that a representation is irreducible if and only if chi phi is equal to 1. So then the induced representation is irreducible if and only if this guy is equal to 1. And so it suffices to study, so assuming that phi is irreducible, it suffices to study how the restriction of the induction of a character goes. It's probably not the right word, but okay. Okay, so this is where things get, I think, a little difficult. That's okay. So two representations, phi and rho of G are said to be disjoint if they have no common irreducible constituent. So if I have two representations, well, so I should say of finite groups, then we have Maschke's theorem, which tells us that these representations are completely reducible, and so they can be broken down into irreducible representations. And if that sum of irreducible representations, if there's no crossover for the two representations, so they don't have any of the same irreducible representations in that sum, then they're called disjoint. So proposition. So representations, phi and rho of G are disjoint if and only if chi phi and chi rho are orthogonal. Okay, proof. So let phi 1 through phi s be representatives. For the equivalence classes of the irreducible representations of G, right? So that means that we can write phi as being equivalent to, phi 1 to some, well, direct sum with itself m1 times for some m1 up to phi s direct sum with itself ms times. And we can do the same for rho, just with different constants. Let's call these n1. Don't be deceived. I wrote phi here, but I could have easily used something that wasn't phi or rho. These are just the irreducible, or at least the representatives of the equivalence classes of irreducible representations of G. So they have nothing to do with phi and rho other than that they make up the components of phi and rho. This is for some mi and I greater than or equal to 0. So from the orthonormality of irreducible characters, we have that chi phi, chi rho is m1, n1, sum all the way up to ms, ns. So take the inner product of the characters of these things. So the character of this guy is m1 chi 1 summed through ms chi s. And then we apply the orthonormality of the irreducible characters, which just means that their inner products 1 if it's the same character and 0 if they're not. And we get this sum. And the right-hand side is 0 if and only if mi, ni is equal to 0 for all I, right? Because these things are all non-negative. And then that's true if and only if phi and rho are disjoint. And that's because mi and ni equals 0. Well, that means that either mi is 0 or ni is 0. And so they will never have the same number of, or they will never have the same constituent irreducible representations. Okay, so it turns out, apparently, according to Steinberg, to be much more difficult to understand this mapping than it is to understand this mapping. H and K are two subgroups. How that could be the case, I don't know, but that's what he says, so we'll go with that. So let's let HK be subgroups of G. then I need to define group action. Let's call it sigma from the product of H with K to SG. And we're going to define it is in this way. So take the elements H and K, and the way we act on G is by HG K inverse. So it's like we're conjugating by an element H, except the latter element is an element of K. The orbit of G under H cross K. So remember, the orbit is just the set you get when you act on G with the entirety of H cross K. This is then the set HGK equals HGK, such that H is in H and K is in K, and is called a double coset. Okay. Maybe I should add of G. So we write H slash G slash K for the double cosets. Just like we write G slash H for the cosets of H and G. Okay, so just like the usual cosets, the left cosets, the double cosets also partition G. And if H is normal and G, then if H is normal G, then H slash G slash H is just equal to the quotient group G mod H. Okay, so I've defined for you this thing called the double coset, which very simply put generalizes the notion of a left coset to two subgroups. Okay, so the next theorem by Mackey explains how induction and restriction of class functions from different subgroups interact. This is where the notation just gets god awful. So let H and K be subgroups of G, and let S be a complete set of double coset representatives. Then for F, a class function on K, the restriction from G to H of the induction from K to G of F is the sum over S and S. So remember, S is the set of representatives of the double cosets. We're summing the induction from H intersected with SK S inverse to H, the restriction of SK S inverse to H intersected with SK S inverse. FS, and now I have to tell you what FS means. Well, first of all, it's an element of the class functions of SK S inverse, and it's given by FS of X is f of S inverse X S. Okay, so that looks terrible. If I knew a way to fix the notation, I would, but it is what it is. Okay. But this is sort of the big result that's going to tell us how this thing behaves. So how do I prove this? Well, there is a kind of correct set of left coset representatives for K and G that we need to select. For each S and S, choose a complete set, call it VS of representatives of the left cosets of H intersected with SKS inverse H. So that's this guy. Okay, well then H will be the disjoint union. So I'll denote disjoint unions with the dot in the middle of the union over V and the set of representatives of the left cosets of well, this guy in H. So V H intersect S K S inverse. Okay, so this is just because the left cosets of this guy and H, they partition H. So nothing fancy going on here. Now HSK is, well, this is HSK S inverse S. I just inserted an S inverse S here. This is equal to, well, this is the disjoint union over V and VS of V H intersect S K S inverse S K S inverse S. All I did was I replaced H with this disjoint union here. And now this is equal to the disjoint union over V and VS of V S K. Okay. So this SKS inverse will do nothing to this intersection. Ooh. I think I may need to think about this one again. Okay, I don't want to focus on this. Let's take this for granted for now, and maybe we can come back to it later. Okay, yeah, I'll come back to it later. So let's PS the set of VS such that V is in VS, and let T equal the disjoint union of these TS things. Then what we have is that G, which is the original group that H and K are subgroups of, is the disjoint union over S and S of H, S, K. And this is equal to the disjoint union over S and S, disjoint union over V and VS, VSK, that comes from here. And this is the disjoint union over S and S, disjoint union over T and TS of TK. That's coming from the definition of TS. And this is equal to the disjoint union over T and T of TK. And therefore, T, well, capital T, is a complete set of representatives. Capital T is a complete set of representatives for the left cosets of K and G. Okay. Now what we have to do is a little computation. This induced map from K to G, F, applied to H, is equal to yes, okay, is equal to the summation over T in capital T of F dot G inverse HT. So this was our proposition we had earlier. This was a sum from I equals 1 to M, and these were representatives of the left cosets. So this would be Ti inverse, Ti, and the other notation. And this is equal to the sum over S in S, the sum over T and TS. So we're just unpacking now. That means the sum over T. Uh-oh. All right, I got another one. Yep. Oh, and this is the sum over S and S, sum over V and VS of F dot S inverse V inverse HVS. The dot. Okay, so again, just unpacking some definitions that we defined. So this is the sum over S and S. And the sum over V and VS, Fs of V inverse HV. That's my definition of Fs. And now V inverse HV is in, yes, this is in SKS inverse. And so we can write this as the sum over S and S, sum over V and VS, actually, I think what I want is something slightly different. To assume Yes, yeah. Okay, this doesn't hold in general. Yeah, this is something that belongs down here. Not there, sorry, but over here. This is a condition of the sum. Wrong place. And this is the same as this sum. Do the restriction, H inverse, sorry, H intersected with SK S inverse to SK S inverse, FS V inverse HV. We're allowed to put this restriction here under this condition. And so this is equal to the sum over S and S of the induced map H intersect SK S inverse to H restriction SK S inverse H intersect SK S inverse FS. Whew. Okay, and that completes the proof. All right, so that is a theorem of Mackey, atrocious notation, and a proof that was probably very hard to follow. It was for me. But from this thing, the point, this is not really the main result. From this thing, we get this nice irreducibility criterion. So let H be a subgroup of G and phi a representation of H. Then the induced map from H to G, phi is irreducible if and only if the following hold. So it's necessary that phi is irreducible. So you can't get an irreducible induced representation from a reducible representation. And the representations res H intersect S inverse of phi, and the restricted map from S inverse to H intersect S inverse phi S are disjoint. For all S that are not in H. There, again, here, this phi S notation just means phi of S inverse X S. Okay, so I think that I am going to refrain from proving this since I'm already an hour and a half into this thing. Okay, proofs in the book. It uses the previous theorem. And this is the criterion. And I just want to point out one thing before we go. When H is a normal subgroup, then again, we have that the set of double cosets is just the quotient group. And H intersect S inverse. If H is normal, well, then this is just H. And so Mackey's theorem, well, actually is criterion. That's this thing up here. In this case, boils down to checking that phi from H to GLDC is irreducible, and phi S, which is this thing where the argument gets conjugated, does not have phi as an irreducible constituent. Well, specifically for S, not in H. Actually, it turns out that phi is irreducible if and only if phi S is irreducible. So all you have to do is check that phi and phi S are inequivalent irreducible representations when S is not in H. Okay, so that's all I've got. Any questions? No, it will not be this difficult, and the notation will not be this awful in the future. I don't think these representations will ever come up again.